Hello, I'm Kidong Lee. Today I will be presenting under the topic Aluminum Kappa Laser Weld Penetration Estimation using Deep Neural Network Classification Models based on Photodiode signal. Many countries are pushing for a ban on the sale of cars with internal combustion engine around 2035. In response, automobile manufacturers are developing and selling various electric vehicles. Accordingly, consumer demand for electric vehicles is expected to increasing explosively. Therefore, the demand for batteries, which are key components for electric vehicles, is also increasing significantly. As you can see above, the welding processes of the battery production processes include resistance spot welding, laser welding, and ultrasonic welding. Because laser welding can achieve a faster process speed compared to other processes, many battery processors are trying to replace other processes. The experimental purpose of this study is to classify the class of penetration depth through photodiode data using machine learning. The material used are aluminum 1050 and kappa 1100, and the equipment used is as follows. We collected the photodiode signal as the input signal. Then we used Trump's OCT equipment WDM to collect our target output, the penetration depth. We corrected the penetration depth data using a real OM data. The collected penetration depth signal was averaged by 70 data, and the photodiode signal was averaged by 5 data, and it was labeled using 5 average sampled penetration depth signals. The photodiode signal was 1-to-1 matched to penetration depth labeling with 500 times series data. As shown in the figure on the right, the average sampled data does not differ in trend from the raw data. This average sampling rate shortens the learning time. We labeled the outputs into 3 classes according to the depth of penetration. Label 0 is the upper plate partial penetration. Label 1 is the transition section, and label 2 is the upper plate full penetration section. This can be seen in graph and photos. In particular, it can be seen that the partial penetration and full penetration of the upper plate are repeated in the cross-section image under the same condition of class 1. In order to compare the accuracy according to the models, the traditional model SVM, deep learning FCN, and CNN models were used. In case of FCN and CNN models, dropout and batch normalization were applied to prevent overfittings. Overall, it was confirmed that the accuracy improved from SVM to CNN. It can be confirmed that this resulted in better result in complex models. Finally, in the CNN models, 98% accuracy was obtained for the classification of the test dataset that was not used for training. After the third convolutional layer of the CNN model, the characteristics of each class were clearly shown in the output of the middle layers. The CNN final model with the highest accuracy was evaluated. The penetration depth was classified by applying the CNN model to the laser welding dataset under the condition of increasing power. As a result, each class was clearly classified at an upper sheet thickness of 0.4 millimeters. Our presentation is over. Thank you for attention. Thank you.